In 1961, the United States Pentagon officially initiated a search that would change military engineering forever. What happens when human muscle meets cold, hydraulic power? The Defense Advanced Research Projects Agency, known then as ARPA, wanted an immediate answer. They envisioned a servo soldier capable of carrying immense loads across rugged battlefields. Rumors quickly spread about the development of a bulletproof human tank. But what was the true, unclassified scope of this Cold War research project? Archives reveal a distinct focus on logistics, not frontline combat. The military desperately needed a mobile solution for lifting heavy artillery shells. Moving massive cargo on naval ships also required urgent technological innovation. General Electric stepped forward to turn this heavy-lifting concept into physical reality. Their engineering team aimed to construct a fully powered, wearable machine. They named the ambitious project Hardiman. Yet, could 1960s technology actually support a walking, human-controlled exoskeleton? The physical blueprints demanded an intricate network of structural steel, hydraulic valves, and early sensors. Every joint required precise calibration to prevent the metal from crushing the operator. As the first metal components were forged, engineers faced unprecedented biological and mechanical obstacles. Could a man truly control a machine twice his own weight without any modern computer processing? The Pentagon watched closely as the line between human movement and mechanical force began to blur. Security clearances were issued, laboratory floors were cleared, and the first official prototype assembly began under strict military supervision. Every single fastener was measured for industrial stress, while lead engineers reviewed complex piping diagrams daily. Technicians worked under dim incandescent lights, soldering delicate wiring harnesses that acted as the machine's nervous system. The hangar hummed with the sound of heavy metal grinding, welding sparks flying toward the high rafters. They were building a giant, yet they lacked the digital brain to guide its massive steel hands. This was a purely analog era of pure brute force. Materials were sourced from the toughest industrial stock available, ensuring the frame could survive initial pressure tests. How much weight can a single human being lift before their bones structurally fail? General Electric designed the Hardiman exoskeleton to completely shatter those natural human biological limits. The engineers established a staggering mechanical amplification goal of 25-1. If an operator lifted a massive object weighing 25 kilograms, their muscles would only feel 1 single kilogram of resistance. The theoretical blueprint dictated that the completed suit must easily lift a total of 680 kilograms. This massive power required an advanced master-slave dual-layer structural system. The operator stood securely inside a lightweight inner framework called the master clutch. This inner structure directly measured the subtle physical movements of the human limbs. Outside this layer sat the heavy, hydraulic slave chassis which replicated the internal force. Giant steel claws were attached to the arms to grip heavy military crates and unexploded bombs. Massive hydraulic pumps distributed fluid through flexible high-pressure hoses at incredible speeds. The design required constant power, which meant the entire apparatus had to be tethered to an external electrical substation. But how do you make a machine recognize exactly when a human arm stops moving? The system relied entirely on primitive analog feedback loops rather than digital software. If the internal valves opened too quickly, the external steel arms would react with immense, destructive speed. Every joint modification altered the center of gravity, making the giant machine highly unstable during initial static lifting tests. Scientists spent months refining the hydraulic flow rates, hoping to achieve a smooth, natural human stride. The military demanded field readiness, but the physical laws of mid-century engineering were fighting back against the blueprints. Each hydraulic piston was custom-machined for maximum displacement capacity. The sheer volume of oil needed to sustain movement required massive steel tanks positioned beside the assembly platform. Cables snaked across the floor like industrial vines. Every valve adjustment changed the system's overall latency, forcing engineers to restart tests repeatedly. What occurs when a multi-ton hydraulic machine suddenly develops an unpredictable mind of its own? As General Electric engineers began powering up the completed Hardiman frame, the dream rapidly turned into a mechanical nightmare. The entire completed apparatus weighed exactly 680 kilograms, matching its own maximum lifting capacity. This meant the machine expended massive amounts of energy simply moving its own heavy steel skeleton. But the most terrifying discovery lay within the analog control synchronization loop. A fundamental delay existed between the human operator's movement and the hydraulic fluid response. This microsecond delay caused the heavy metal joints to violently overcorrect during basic operations. The entire exoskeleton would instantly begin to shake, vibrate, and swing uncontrollably when activated. Internal engineering logs from 1969 explicitly document these terrifying, sudden mechanical failures. One official report states that when the shoulder joint received hydraulic power, the arm flew open violently while the Dursek malfunctioned completely. The machine was essentially a trap capable of snapping human limbs like dry twigs. How could they fix a structural feedback loop without modern microprocessors? They simply could not. The physical system lacked the computational speed to balance itself safely. The massive hydraulic pressure frequently caused seals to burst, spraying hot oil across the laboratory. Every attempt to stabilize the legs failed, as the feet would dig violently into the concrete floors. The dream of a walking soldier was trapped inside an immobile, shaking cage of steel. Every activation test resulted in further damage to the structural joints. The hydraulic lines hissed and groaned, revealing the strain of supporting such immense weight without electronic dampening. Technicians scrambled to shut down the main power supplies during every surge. Would you willingly step inside a 600-kilogram metal suit that might violently tear itself apart? The engineers at General Electric reached a definitive, unanimous decision. Absolutely no human being would ever be placed inside the full Hardiman prototype. The risk of lethal mechanical crushing was simply too high for any test pilot. Because of this severe safety hazard, the complete, full-body exoskeleton was never once turned on with a person inside. The project was completely fractured, forcing researchers to change their testing methodology. They physically detached the right arm mechanism from the main chassis for isolated laboratory experiments. This single, decoupled arm was safely bolted to a heavy stationary test stand. Surprisingly, the isolated mechanical arm successfully managed to lift 340 kilograms during controlled trials. It proved that the hydraulic power amplification theory was fundamentally accurate. However, an isolated arm cannot walk into a battlefield or load a supply plane independently. The lower body remained completely useless, incapable of supporting its own massive structural weight without external cranes. Millions of military defense dollars had been spent, yet the machine remained completely paralyzed on its laboratory mountings. The Pentagon grew increasingly impatient with the lack of mobile progress. The gap between theoretical science fiction and physical reality had become an unbridgeable chasm for the military. The test stand became the final sanctuary for the prototype's surviving parts. Engineers monitored the isolated arm with clinical detachment, knowing the dream of a full-body suit had stalled. Every data point collected served as an autopsy for the failed design. The dream of a mobile giant was relegated to static iron pillars and scattered hydraulic components. When does the military finally decide to abandon a multi-million-dollar technological dream? On August 31, 1971, the official funding for the Hardiman project was permanently terminated. The United States military and General Electric formally closed the books on the historic endeavor. The high-pressure hydraulic lines were drained, the electrical tethers were disconnected, and the prototype was wheeled into storage. It never saw a single day. It never walked across a laboratory floor under its own power. The total lack of digital computing and lightweight materials had completely doomed the 1961 vision. Decades later, the Defense Department completely abandoned these massive, heavy concepts. Modern DARPA projects like Warrior Web focus on flexible, soft textile suits designed to prevent muscle fatigue. The era of the giant hydraulic human tank was officially over before it even truly began. The remnants of the project remain as archival photographs and dense engineering reports. The 1961 exoskeleton project did not create a super soldier, but it defined the exact boundaries of modern robotic control systems. The legacy of Hardiman exists only in the history of failures that paved the way for modern robotics. it remains a monument to a time when engineering imagination exceeded the capabilities of the era's hardware. The lesson learned was foundational for all future research. The project, while officially a failure, provided the necessary blueprints for eventual success. Scientists look back at these heavy steel frames and recognize the birth of modern biomechanical research.